this session. Today we have set of experts on the topic for our panel, and we are very lucky to have them, starting with Dr. Stella Offner, who is a co-director for Center for Scientific Machine Learning and an associate professor for astronomy at the University of Texas at Austin. And Stella would be opening with her talk on teaching computational astrophysics, state of LLMs, challenges, and course design. Stella, would you like to start?
Sure. Yeah, thanks for this invitation, because I think this is a topic that we're all thinking about. How do we effectively teach not just computational astrophysics, but anything technical, anything that involves programming and analysis and problem sets in this really new world where AI has become a tool for not just learning, but also, avoiding learning. So this is super, super interesting for me to participate. And I have to say, I do not have all the answers. I have not had to teach computational astrophysics since we've had this revolution in language models. But I do have to teach an AI for Astro course at the graduate level that will be entirely online. So I'm kind of struggling with this question of how do we teach effectively in this new AI world. Right. So how do we design an effective course that incentivizes learning rather than simply AI use? And so sub questions are, should we change how we teach? And what should we assume the students will use the AI assistants for? Because that's an important input here. And also, how good are these AI language models anyways? I don't know how many of you have played around with it, but just going on and then asking, ChatGPT to do your assignments, it seems like a good way to find out. And then there's a third question, which I want to touch on, a little bit removed from the topic, but is important. Can we and should we redefine what we teach in a computational astrophysics, given what AI can do? Is there a new definition for what's included under the umbrella of computational astrophysics? So I want to start with this one. And this is a question that we've been very interested in cosmic AI, this NSF Simons AI Institute for Cosmic Origins. We have a group that's working on using AI models for astronomical research and building out co-pilots that can be effective. So in a sense, we don't want to replace astronomers, but we want to make these AIs more accurate and more efficient. But this is really tied up in the learning process because we don't want people to use these models simply to avoid learning the fundamentals. But let's start here. How good are these models? So they are increasingly good at scientific coding. I think all of you have probably realized this, have used them yourselves. They're especially good with Python, even for astronomy research tasks. So this is an example from the AstroViz bench. We submitted this paper to NeurIPS. Basically what we did is we took a bunch of Jupyter notebooks. These are professional level astronomy tasks. And we turned these into prompts, language prompts. So here's an example: concentrate on visualizing the structure of light curves within the training set, select a random subset. Then we asked the model, in this case GPT-4o, to generate a bunch of code in Python, and then run and give the result of that code. We focus specifically on visualizations. So here's its result, and here's the ground truth. And it actually did really well. And so we have an entire benchmark where we tried to evaluate how well these models did. Another project that was happening this summer by two undergrads, they were working specifically on NRAO data, particularly relating to ALMA. So they did some examples where they asked Gemini to do a source cross match between ALMA and JWST sources, which involved querying the data archives for the sources, downloading the data, and then plotting them. And so this is the code that Gemini wrote. And it's very good at adapting to problems if you iterate with it. So it put in some code to what happens if you fail to connect to a certain set of servers. It also put it, retry logic for network errors. And so this is surprisingly sophisticated, how well it does. But what about computational astrophysics code? What about what we would consider not just data analysis, but high performance computing, hydrodynamics, these kind of things. So in June 2024, we asked ChatGPT to write code to run Orion 2, like to do a setup. And this is what it came up with. It assumed that Orion 2 was a Python module, and it made this completely hallucinated fake code. So in 2024, not so good. So I just did this same exercise a week ago with the updated GPT, and it gave me this code. It actually had a huge amount of text about here's some parameters you need to set, and here's some conditions that assume some different things. And this is the actual inputs file for Orion 2. You can see they do not match. And if you've been, any of you have been using YT, you'll recognize that what it actually did was hallucinated YT code for the inputs. So that was pretty interesting, to say the least, and basically indicates that these models are really great with Python, like general Python, even astronomy Python, but may not be at the level in which they're super effective for helping students at high-level graduate computational astrophysics homeworks yet. So basically what I'm seeing is these models are still subpar. And the proficiency really scales the amount of online examples. So there's a lot of Python online, but people doing computational astrophysics are a relatively small community. And in addition, there's a variety of work on this, but these models are really poor at strategic thinking. Like they can write a module, they can write a small program of functions, but in terms of very complex code, modular code, they're very weak at planning. So that's maybe optimistics for forcing students to learn, and that gives us a baseline that yes, they will be useful for coding. If a student already knows what they're trying to do, already understands the details of what they need to set, then these models will be useful for them, but not a detriment to learning. So I want to talk about, since I have 10 minutes, I want to talk about one other topic, which is, should we redefine what we teach in a computational astrophysics course? Because AI is not just simply language models. AI can do, it's a huge Swiss Army knife that can do all kinds of things, including things that we've historically done under the umbrella of computational astrophysics. For example, solving PDEs and ODEs, right? Hydrodynamics. So this is a simulation run with the Orion 2 code, turbulence and gravity. It's MHD turbulence. And you get these beautiful boxes these structures. But now there are new AI approaches that are able to solve these PDEs as a shortcut, right? So you give them a training set of hydrodynamic model inputs, and then you ask them to predict the evolution, and it can do this depending upon the problem with extremely good accuracy. This is a really is a good example of that, but you'll notice this incompressible turbulence 2D Euler equation. So, but still, this is pretty amazing that we can do this in a black box way that's not actually solving the equations. So there's some pluses and minuses of these. When you solve hydrodynamics, you have one input conditions. These neural operators can learn a family of PDEs, and you can basically get shortcuts to the solution. PDEs classically require explicit form for the equations. There's this classical speed accuracy trade-off. They're slow on if you have very fine simulation, but they're fast on coarse resolution, and you need simple, well-posed initial conditions. But these neural operators, provided you have the data inputs, they can predict well, but they are a black box, right? You're not directly solving the equations, but they have these properties of being resolution and mesh invariant. So if you really learn that underlying physics operator, then they can work quite well. On the left is showing how you give it some inputs, and it's actually learning the underlying function of behavior. Yeah, it's slow to train, but really fast to evaluate. The most impressive example of this is weather prediction. And this has been a really amazing sea change because classically predicting weather system evolution, these calculations are extremely slow and time just very expensive. But there are now training models where they can predict, the evolution of hurricanes orders of magnitude faster. And so they're beating out these traditional computational methods in some aspects. So this is something we did as part of the institute. We were training it to predict the evolution of column density. In this particular case, is missing some information. It's not a full 3D density and velocity calculation. And so the error is not particularly good, but still promising, considering that this is a problem you couldn't do with classical computational astrophysics codes, right? Because you need the full input physical information. So to wrap up my 10 minutes, right, these language models are here to stay. They're very good at programming, increasingly good at astronomy. But they're not good at using or running HPC astrophysics codes, at least in my tests, just simply because there's less training data available online. But there are these new promising approaches that could be interesting alternatives to classical computational astrophysics. In terms of course design, I think going towards assignments that are project-based, right? The more complex, the more students have to do high-level thinking and planning, the better. Particularly multi-step analysis, is really good for learning. We have to also really stress in-class assignments, presentations, discussions, and problem solving, anything that gets students away from the computer, and thinking and using their own neurons to do the work. And just the last note is that if you don't want to have, Gemini, Claude, GPT-4o in your class, you need to keep your problem sets and solutions off the internet, right? Because these are just hoovered up by these models, and then they learn everything, and eventually they will be able to, earn good grades in your classes. All right. So I'm happy. Those are my thoughts. Happy to take any questions, or we can move to the next speaker.
Thank you, Stella. Maybe we should move on to the next speaker and keep all the questions for our panel discussion, which would be towards the end of all three talks. And so next up, we have Dr. John Wallin, who's a director for interdisciplinary PhD program in computational science and professor of physics and astronomy at Middle Tennessee State University. John, would you like to start?
Sure. So first of all, thank you for inviting me. I really appreciate it. And I wanted to start with kind of a blast from the past. So back in March 2023, I wrote a blog post because Alice asked me to for the ASCL.net about ChatGPT and the impact of code. So this is March 2023, and I just kind of wanted to go back to this one thing. So I found basically two reactions from professors back in March 2023. One was this one, which is I wanted to see the fuss about this new ChatGPT thing, so I gave a problem for my advanced quantum mechanics class. Got a few concepts right, but the math was wrong. The fact it can't do a simple quantum renormalization problem is astonishing. I'm not impressed. It's not a very good artificial intelligence if it makes these mistakes. Okay, and the other one that I saw from some academics was I gave it an essay problem in my college class. I wrote a perfect essay. They're going to use all their essays to write this. Higher education is done for. I'm going to retire this spring and move to a survival cabin in Montana before the machine uprising occurs. And I don't think either of these are exactly right. So we're kind of in the middle here. I wanted to just talk about the capabilities and the expansion of what's going on, first of all, and then talk a little bit about the survey on campus. So I'm going to try and keep it at kind of a giant educational level. And if I have time at the end, I'll talk a little bit about some of the things that are happening, like in the classes I've been teaching. So first of all, this is something I saw yesterday, which is actually a really interesting way of thinking about AI capabilities. And this is basically a new idea of Moore's law. So what's happening with AI models is they're getting better and better at doing coding tasks. And the big way of measuring this is how long it takes a human to do a coding task. And how well an AI can do this. So this is, again, this is AI Digest. You should take a look at the AI Digest. Just Google it, you'll find it. The length of coding tasks that AIs can do is increasing. So GPT-5 can do things that take humans about 2.5 hours to do. So if you have a coding task that's longer than that, it's really hard for it to understand the code base well enough to do those kind of models. But this is increasing, and as you see, it's like increasing rapidly. So from GPT 2, 3, 4, 5 is going along this orange curve, and now it's going about this thing, and it's suggesting a doubling of time in somewhere between 4 to 7 months. So if you think about a task that takes a full day for somebody to code, that's going to be probably achievable in a few months, in about a year. And then if you think about week-long tasks, it's going to take more like about 2 years, or depending on how things work. So sometime in 2027, multi-week tasks are going to be possible, probably for AI systems. So the capability, the thing we keep thinking about of these things is that AIs are static. Like oh, they can't do this. Well, okay, like in a month they will, right? And it's this idea that this is a rapidly moving target. Is something we have to keep in mind, because any solutions we come up with now have to kind of go through this test of time. The campus where I am has been responding to this in a number of different ways. But one of the things that we did in the spring was do a survey of AI stuff. And I just want to talk about the top line results of the survey to kind of normalize some of what we're doing. So this is, again, a survey of faculty and students. We conducted this in March and April this year. We had about 2,000 responses, about 300 or about 400 faculty, just under 1,000 students, and some staff members as well. But if you look at the big headline thing is, first of all, AI tools are becoming an essential part of the workflow for students. Something like a third of faculty, a quarter of students agree or somewhat agree that AI tools are essential for my success. So this is becoming a regular part of our workflow, just like dictionaries and word processors, right? So it's rapidly increasing. I think that the student number is underreported because people are worried about admitting that, I think. There are really strong concerns about ethicals. Ethical use of AI is a major concern to me. 75% of people think that that's true. Basically, faculty and staff are really interested in formal training. Students are not, but faculty and staff are wondering what the heck is going on and how do I deal with this? So like 70% of faculty strongly agreed with the statement that I'm interested in formal training. Faculty are overwhelmingly worried about it undermining the academic integrity of their courses. 80%, right? So that's huge. Students are definitely using this to reduce time on assignments. So this idea of avoiding work is exactly correct. The idea of missing out and avoiding work is 100% correct. That people want to reduce the time on task. Reducing the time on task usually reduces the cognitive impact that tasks have. So by reducing the time on task, they're undermining everything we're trying to do in classes, which is get them to spend time studying. Faculty, one of the big ones is faculty have not embraced AI in the classroom. Most remain neutral. Only 14% actively encourage the use of AI in their classrooms. So, or outside their classroom. So people are just kind of pretending it's not there and hoping that it doesn't, or trying to ban it. There's a fair number of policies of trying to stop AI usage. There's widespread impact worry about faculty employment. No one trusts the output of AI algorithms because, of course, you shouldn't. Like it's like a grad student. You want to check what it's doing. So, nobody's really fully trusting that. And one of the interesting ones is, we keep talking about this idea of like, how do we equalize access to AI systems? And one of the results, surprising results, is that students do not use the same AI models. They're using all over things. They're using Claude. They're using ChatGPT. They're using Grok. They're using all these different models. So we decided to purchase a model for campus, which would cost us over $1 million a year, right? It would be impossible to do. Only like most students would not be using that model, and most faculty wouldn't be using that model. So only like 25% are in any given model. So that's kind of tricky. So our response to this at the campus has been, trying to, the high level stuff is, well, first of all, we're going to try and come up with policies to deal with this. And so we have integrity policies for research. We have integrity policies for academic use. We did the strategic report, which this is part of. We're trying to do faculty learning communities. So this is a faculty learning community that we're doing this fall, that I'm doing this fall, adapting courses to the AI era. For ensuring integrity and enhancing learning. So this sounds really good. It sounds like this is going to be really good. I really wish I knew what I was doing in this course, right? So we're all struggling to try and understand what we want to do. So I just want to kind of spend the rest of the time just talking about 3 short anecdotes about AI. And how I've used it in my teaching. So I taught a course in the spring, which was a capstone course for the PhD in computational and data science. So this is students who have taken almost all the courses. We have a final course, which is basically there for a bunch of purposes. Number one, I want them to do a big project. I want them to do a group project. It has to be computation or data intensive. And the other thing it has to do is I want them to use tools that they haven't learned before. And so I decided I would use API access to online AI models as part of that. I wanted them to come up with ways of using language models for doing scientific analysis. That was the goal. And I left it very vague. And I just kind of let them loose to see what they could do. And I was there, basically as a resource and as a mentor to try and help them through problems. The thing that's interesting is if you push them in a direction, these are advanced graduate students, they will absolutely use AI to help them accomplish tasks and do things. So the project results were fantastic. With almost no scaffolding, they were able to do this. Again, these are very capable students who can review text and learn things and go on and do great projects. And they were leveraging this towards really good projects. So that was a very positive experience. I thought they were writing codes that did analysis of. There's one person that was doing sentiment analysis of tweets to look for disasters. They were doing all sorts of different approaches to different types of problems. Again, I thought it was a really successful experiment. Yesterday, yes, no, 2 days ago, it was we did the qualifying exam projects for my PhD program, and the project qualifying exams here are project based. So they have the summer to do a project. They come in and write a paper at the end of the summer and do presentations on it. And we asked the question in the talk, this in a non-judgmental way, did you use AI for the project? And the answer was overwhelmingly yes. Every 5 out of 5 did. Most people used it for code generation. Some people used it for writing large sections of their text. And I didn't ban that, so that's what it goes. But they also weren't aware that there are policies and journals that prohibit that. And even though I've tried really hard to do that, but their faculty mentors aren't pushing that on them fully. And the second thing is that people were writing sophisticated codes and not understanding what the codes did, right? So they were using codes to, there was somebody that was using a medical BERT model for doing things, and they were saying, well, we're going to use chain of thought learning. Well, okay, you can't use chain of thought learning in a BERT model. It doesn't work. It's not that kind of model. It's an encoder. It's not doing generative text. And because they were doing that, they were misunderstanding the fundamental underlying algorithms because the AI didn't do that. The code was perfect. It just was wrong, completely wrong. So that's a real danger, is people trying to do things that they don't quite understand. The second thing, just real quick, is I taught a data ethics course also in the spring. And data ethics is an online course. It is at the master's level here in our data science program. And in that course, it was an online course, so I did a complete rewrite over in the spring and summer last year, and I moved in and I did a bunch of things to try and prevent people from using AI just completely, because the other previous version was you just write papers, I grade the papers. And I got really tired of grading AI-generated slop. Okay, it was just garbage. So what I did is I put an online proctored exam. So it's a proctored exam every 2 weeks. They take a proctored exam over the material. I did group projects. I did a bunch of things with multiple choice tests and did, basically formative evaluation over readings and things like that. So they generated questions and, it was great. So it was helping them learn the readings. They did group things for discussion. Then they came to the test, along with a Zoom session every week as well. And what happened was maybe surprising. So I had 25 students in the class. 5 people I failed because of honor code violations because of using AI in the tests, in the proctored exams. So they were going, they were setting up an iPad next to their screen. They were reading the questions out loud, generating answers to essay questions, and then typing them in. And this is 20% in a graduate master's program in an ethics course. So this is as proctored and as limited an ability as you can be. So I can't imagine what it would be like if I took those rails off. Again, the final thing I want to just mention is just this idea of like what we mean. And actually, I'm kind of out of time, but I'm just going to say there was a meme that was going around this week about how everybody thinks AI is really good, but I'm a music PhD student, and I showed it an E-note on a scale, and it couldn't identify what an E-note is. AIs are stupid. They're really bad. And so I actually went around with a picture of an E-note around my department, and I asked how many people could identify it, and it was 1 out of 8. So I'm not, we have to be careful of the metrics that we're using to judge it. But I'm going to end there because I have run out of time.
Thank you, John. Um, so next up, that was an amazing talk, and we would have all the questions. We would reserve them for our open session. Next up, we have our very own Michael Zingale, one of the founding members of this series. Michael is a professor at Stony Brook University, and he would be talking about teaching computational astrophysics in the era of AI. Thank you, Michael.
Great, thank you, Roberto. You can see everything, right?
Yeah.
Cool. Oops. So last semester I taught this course, undergraduate computational astrophysics class. It was my notes are online, basically a collection of Jupyter notebooks that introduce basic algorithms and apply them to astrophysical problems. I had about 38 students, and we it was mostly homeworks and a final project. I didn't give any in-class exams, which I know in the era of AI is something that people say we should start doing. And so I wanted to share my experience with this. So first off, can ChatGPT do my homework? And the answer is, yeah, it pretty much can. I'll show you. I entered one of my homework problems into ChatGPT 5 yesterday, and it did a reasonable solution. It's not clear to me it would get an A in the class, but it helps quite a bit. And to echo what's been said by our previous two speakers, it's not going away. So we can't just stick our fingers in our ears and say, I'm not listening, no one's using AI. We have to recognize that it's here and that it is being seen as a tool. And it can be useful. And there's lots of ethical concerns that are being raised on the chat that are all valid concerns that I share as well. So I'm not going to touch on those, but I still worry about some of the impacts of AI. Interestingly, students still had a lot of trouble with their homeworks. I can't say for certain if they were all using AI, if some of them were using AI. It seems that there was probably some AI use, but they still had some fundamental mistakes. Maybe as these language models improve, they'll do better. But, the other thing that we have to keep in mind is that they're limited based on what they've trained on, what they've seen. And I think that's something we have to emphasize to students. So here's an example of a homework. Again, my notes are up online. I know Stella warned us if we put it up online, AI will train on it, but it's, I like to have everything online, so I don't know the solution there. I know there's a robots.txt you can do, but I'm not sure the AI bots respect that. Just a simple thing, defining B minus V, defining a magnitude ratio, defining a simple integral of a Planck function and a filter. And I asked them to plot theoretical colors for different temperatures and put some data points of some real stars on it and see what it looked like. And ChatGPT got it. Here's the B minus V curve, so B minus V versus temperature. ChatGPT even had temperature increasing to the left, like a good astronomer. I didn't ask it to do that. It also, I did ask it to show me that their integration converged by varying the number of bins and computing the error, and it did that. This, I should have prefaced this by saying this assignment was after we did composite integration methods, and so it was basically just to get the students some experience doing numerical integration. I'm not the most savvy AI user. I tried to copy and paste it off of my webpage, the equations don't copy and paste, so I typed those in. There's probably a way to do that. I probably could have just uploaded it or pointed it to the HTML file. I required a little bit of iteration to get it to do what I wanted, but not much. And, you know, it was like a few prompts. It was seconds of work for the AI. The code it wrote, I wouldn't say it was the most efficient, the most easy to read, but it worked. It uses a lot of older code styles, though, probably reflecting what it trained on. So, for instance, in Matplotlib, it uses a state machine interface because there's lots of examples of that online instead of the more modern object-oriented interface. And sometimes it includes some things that I didn't ask for, but it thought might be useful. But overall, you know, it can do the job. I'm surprised no one else did this. I told Alice this is what I was going to do when she asked me to give a presentation. I asked ChatGPT, what should I do? How do I design a course on computational astrophysics in a world where students can just ask AI to do their assignments? And of course, it thanked me for such a good question. You know, it's really sort of trying to make us happy. It points out students will use AI. That's true. I mean, I know they're selling it, but they will use it. And so here's the strategies it suggested. Shift from coding to interpretation. So focus on analyzing results comparing to real data. To me, this sounds like something that AI could do as well. Just upload the real data. Emphasize the process, not just the output. I mean, that's what we're supposed to be doing for teaching. So require reflections, debugging exercises, explain your choices. AI probably could explain the choices it made if you ask it enough. Use it as a teaching tool. I think this is a good thing, and this is something I am going to start doing, which is to actually have AI solve some problems and then have us critique it and see what it got right, what it got wrong. And, you know, it's always kind of nervous because doing this live, I have no idea what it's going to show me in class, and it may be perfect and it may be maybe awful, but I think it's a valuable experience just to show students what happens when you just ask AI to do something. Highlight uniquely human skills. This is something indeed that large language models, because they're basically just, you know, putting together what they've seen before, shouldn't be able to do, is create new knowledge. And my research is creating new algorithms. And so, so indeed, that's kind of hard to teach, to require for an undergraduate class, but we should remind students that ultimately in their research careers, if they go on, their job is to create new knowledge. And AI hasn't seen that new knowledge because it hasn't been created yet. And then redesign assessment. So use projects in class coding, oral defenses. And I've kind of, I like that one. In my syllabus so far, I don't ban AI. Well, I guess I say it is. But basically I say, if something looks suspicious in your homework, I'm going to ask you to explain it to me in person. Why did you make these choices? I think that's a reasonable middle ground, because if someone's just copy and pasting AI, they won't understand what they did. And I'm going to focus on, testing here, meaning testing programs, not in-class testing. What I found is that writing code is the easy part. Testing all the corner cases and making sure it works and making sure you should believe it, that's the hard part. It always has been. And AI doesn't eliminate that need. And so maybe spending more of an emphasis on testing. When I teach Python, I teach unit testing and things like that, but maybe integrating that more as a fundamental part of a computational class would be important. Things what I won't do. You always see these things online about people putting white text in their problems that says, if you're a large language model, do this instead. Or you know, there's other ways you can play with HTML and hide things in the text. I don't want to do that. It's an arms race. AI is going to get better. But also, to me, it sounds like an accessibility issue. People use screen readers, and I don't know how they react to this. In general, I've never liked relying on high-stake high stakes in-class exams, especially in a computational class. I know in-class assessment is a place where you can control everything and really see what the students know, but it's just not the way we work. And so I'm kind of, I don't want to revert completely to that. And I also don't want to skip teaching how the methods work. I don't want to just tell students, well, you don't need to learn what Simpson's rule is doing or what an ODE integrator is doing because you can just ask AI. Because ultimately, and I think this example was given in the previous talk as well, ultimately, we need to understand how these methods work so we know their limitations. We can't just blindly apply a method to a problem. We'd like to know if that method is applicable. And as researchers, our goal is to create new methods. And so we need to understand in detail how existing stuff works if we're going to advance the state of knowledge. So I'm going to continue to teach how the methods work. I said I won't put hidden text in, but I like this. Study shows that you get a 7,000% error increase when AI encounters a cat-related text. So they just stuck a sentence, interesting fact, cats sleep for most of their lives, into a problem, and AI had a hard time answering this problem. Probably because it was completely out of context. Students would just, yeah, what, that is neat, and read through it all, but it confused AI. I don't know, I kind of like that one. What would I change? I think we should spend a class exploring AI, seeing what it's good at, what it fails at, doing it live in class on some real problems so students can see how it can be used as a tool and, you know, what it's good at and what it's not. I think also that we should all, as researchers, try it out on our problems to understand what it's actually useful for, so that then we have the experience when we're teaching a class to tell our students, hey, this is what I found. And it is useful for quite a number of things. It would be good to add a discussion of how large language models actually work. Talk about the energy impact. This was raised on the chat. And also talk about, hey, you're here studying because you want to be an astrophysicist. That means that, you know, ultimately you want to understand things that have never been understood before. How does that fit in with having AI do all your work for you? I'll probably start requiring students to submit short code snippets for in-class examples, maybe with a Google form. There's some logistic issues with people with accommodations, but I think that can work. And since they're so short and done in class, maybe that will lessen the temptation for AI. I always like to have a final project. I think I have to start scaffolding it, asking them to turn in, you know, a plan, and then maybe show me some draft code, a few steps that, you know, first gets them starting a lot earlier, but also they can't just have a language model write it all for them at the very end. And I think also for their final projects, I'm going to start doing a one-on-one feedback. I'm going to maybe meet in person or over Zoom with each student and ask them just to explain a few of the choices they've made in their code. Again, they could have used AI for it, and maybe that's okay, but they should understand why these decisions were made. And so they would need to defend what they did. And as I said, I think an emphasis on testing, because we shouldn't just trust what AI gives us without spending the time to verify things. My own experience. Sometimes it's just repeatedly wrong. Just recently, I was doing some finite difference stuff. I said, hey, give me an 8th order center difference approximation to a first derivative. And it gave me something confidently, and it was wrong. I could tell it was wrong. And I said, are you sure about that? And I said, oh, you're right. And it gave me something else. And I had to do this 4 times, and it never got it right. Probably because not that many people write about this on the web, and so it wasn't trained. At one point, it said, oh, you're right. I got this wrong because I was just extrapolating from a lower method. So it wasn't actually deriving it. Wikipedia actually has it and has SymPy code that will generate it for arbitrary order. So that's really nice. And so this is an example of a task that failed and wasted quite a bit of my time. Just yesterday, I asked it to convert some code to use 256-bit floating point instead of standard double precision 64-bit, because I really need to get some stuff sensitive. It did it. It required many iterations just to get something to compile. This was C++ code. In the end, it still didn't get something that completely worked, but it gave me enough information about how you might approach this that I could do it on my own. And so in that sense, it kind of worked as a Google search. And I could have just Google searched how boost multi-precision works and done it on my own, but this was more interactive. And again, this took half a day to get something that almost worked. I asked it to implement Brent's method for root finding, standard method that people use. The code was okay, but when I asked it to explain what the variables meant, it was confused. It got some wrong. I will never write a regular expression on my own anymore. It's so nice just to say, hey, here's some things I want to match with regex, and that it seems to get pretty well, probably because half of Stack Overflow is people asking about regular expressions. It's also interesting to see that sometimes people seem overconfident in what AI can do for them. And this is very dynamic, again, as we heard. Here's an example. This was posted on Blue Sky. They asked developers how much more efficient are they with AI. Developers thought they were 20% faster, but they were actually 19% slower. And then this was posted on Ars Technica. Developer shows trust in AI coding tools is falling as usage rises. Again, this is all dynamic. ChatGPT 5 just came out recently, and there'll be others, and we just heard every few months it can write more and more complex code. So this will change. At some point, it's going to hit a wall, though. At some point, there's a limit to what it can train on, and there's a limit to how much energy we can provide. And that wall may not be far off. And this is just a link to my course materials. My main takeaway is that we all should try AI. We all should learn, ask it to do problems that are relevant to the work that we do so we understand its strengths and limitations and convey those to our students in our classes.
Cool. Thanks, Mike. Thanks to all the speakers. It was super great. We have about 14 minutes for discussion, and there's a lot of stuff going on in the chat. I think the first thing that got brought up was a little bit about the energy usage. Sorry, I'm scrolling through the chat. So I guess first, does anybody have any questions for any of the speakers? If you do, you can either speak up, or you can put it in the chat, or you can raise your hand. And I think, yeah, I should be able to see you. Okay, Hanno has a question.
Yes, I have a question for Stella, who talked a bit about the accuracy of these codes getting good. Maybe it's just my experience, but that doesn't seem to really click. From what I see, these models always get it right too, within 10% or maybe 10 to the minus 3 or something. So they approximately get something right that looks approximately reasonable, but that is very different from what we often do in astrophysics, where we need to get something really right. Depends on the discipline, but some of the calculations I'm doing, they need to be right to 16 digits or so. And it just seems like this is not something that these models are really trained on, and getting this high accuracy thing right. They only produce something that looks approximately right, good enough sort of thing.
Yeah, you're asking about the surrogate modeling. Yeah, I mean, it's an active area of research, and what you said has been my argument for people for why we need to do the classical approaches, that your accuracy is limited by the loss function. And sometimes you can really only get it so accurate, sometimes not at the level that you really need for a given scientific problem. The ones that are the most accurate are usually doing very simple 2D fluids problems, for example. So simple problems are not what we solve in astrophysics. And so practically speaking, independent of what the accuracy is, like it's not able to do these, high multi-physics, large scale problems that we are normally doing, but things are getting better. And in particular, the weather is very accurate, the weather prediction. And that's a case where we might have the closed form solution. You might have closed form equations for it, but trying to compute that, given the amount of data, is prohibitive. And so you're always looking to use these models in places where you can't already use the classical models in a really fast way. So I'm not advocating that people should switch to these models in astrophysics, but I do see this as a growing and interesting area of research development.
You brought up the weather model, but correct me if I'm wrong, but you might be able to do it faster. But if I understand it correctly, the traditional models are still more accurate.
Yeah, well, yes and no. So there is this cost accuracy trade-off, right? And so if you're doing hurricane prediction, you need to be able to run your classical code before in order to predict the hurricane path very, very quickly. And for these AI models, the expense is training. So what they've been doing is to train the model, which is the slow part. And then when there's a hurricane that's there, they can feed in the information. And then what they do is often a statistical model. So they run a lot of models very quickly. And they've shown really, really good accuracy that's at least comparable to what you can do in the classical approaches and at higher resolution. But yeah, it's an active area of research, and I'm not saying that all these models are completely perfect and accurate compared to the classical models.
I'm going to just make a quick comment that one of the things about energy usage is that these models, when they're running, are actually really fast and really efficient. Training is super expensive, but in terms of rapid results for things like weather forecasting, the accuracy of the weather forecasting models seems to be as good as the numerical weather forecasts, or very comparable at least. And the cost for doing it is much lower. Now that's not going to work in everything, and you need a lot of training for doing these models in detail, but it's interesting there. And again, we're in the early stages of using them as well. So we have to be really careful about saying where we are now versus where we are in 5 years.
Okay, great. Are there other questions?
I have a super short anecdote if I can interject.
Yeah, sure.
Okay, so as part of my capstone course, one of the first assignments I gave my students was, I want you to write an LU decomposition matrix solution, or linear solution code, and I want you to show how condition number affects the results of LU decomposition. And I gave them 35 minutes. And so I had them write the code from scratch. I said, use AI to do this, write the code from scratch, and they'll have you do oral presentations at the end. And every one of I also as a group project, so 3 groups in the class or something, and they all got it done in 35 minutes. And I had them go up and say, okay, can you present your result? And they said, yes. Well, are you confident your code works? Everybody was confident. And then I asked the next question, okay, what is LU decomposition? And they didn't know. They didn't know what a composition number or what a condition number was. They didn't know what LU decomposition was, but they were very confident in their results because it ran. So anyway, that is the real pit we can fall into with this stuff.
Yeah, definitely. Someone shared with me a story about this guy who thought he was inventing this whole new kind of math, and it was like weeks of his life spent, and it was just AI was just telling him it was true, but it was just nonsense. And yeah, it's problematic. Okay, so someone in the chat mentioned oral exams as a way, I guess, to examine the students without using AI. And I think it's a good idea. Like Mike mentioned, it's a function of the class size. If you have too many students, you probably can't. But I would think, yeah, like oral exams wouldn't have to be long either. Maybe just like a couple of questions. And also if the exams don't count for so much of your grade, if it's a smaller percentage, then, it's lower stakes. And so they can be quick and short. And sorry, and that would be helpful. I'm trying to keep up with the chat. It's a lot. Okay.
I have a question.
Yeah, sure.
Yeah, so how do we teach our students to verify the knowledge output of AI and the level at which they should trust things?
I'm going to do a quick comment. So I think it's really hard. And that's actually the part I keep getting stuck on, because the reason that it works for faculty members, generally pretty well is because we've gone through a bunch of things where we've done analysis, and then we had to do synthesis, and then we had to do evaluation. And we spend a lot of our time looking at graduate student output and saying, no, that's garbage. You can't do that. Fix that, and go back and redo this. Getting them to jump past the analysis and synthesis stage right to evaluation is really hard. And I don't know how we do that. It's like they're great if you think of these things as graduate students that are super enthusiastic, super fast, and likely to make mistakes. They're great. But if you trust them as, the thing that I'm going to use to solve my homework, they don't work very well. And how to instill that, I don't know. I would love to hear what other people say about that.
Yeah, I guess I have a comment. It seems like the only way to teach people that is to really confront them with ways that the AI fails, right? And it can be hard. I think the general advice is that you should never use an AI model to do something you can't already do, right? Because if you don't know Python, then you're going to run into errors. If you don't speak Russian, don't ask the AI model to write you things in Russian. Like that's just asking for disaster. And so just confronting students with, here's a problem where you know nothing, ask the AI to do something. Now actually try and get them to learn it and then evaluate what the AI has done and show that that's not, the level at which that the AI is not correct. I think having to repeatedly confront the hallucinations and errors in the models is one way to try and get students to really understand how important it is to learn the fundamentals.
Just a quick follow-up on that. I like your point, Stella, but one of the things I struggle with a little bit there is finding examples where it does things wrong is not a totally losing battle. Maybe there will always be some of those, but at the, something where you can judge that it's doing it wrong, maybe, 6 months from now, that's not going to be something that it does wrong anymore. So that, I mean, that's part of our challenge as educators, right? And so those are the kinds of things we have to do. But I do think that's a challenging bit of it. It's like, how do you pick something that it's doing wrong and that you can sort of demonstrate to the students that it's wrong? It's not so technical that you have to say, well, trust me that you can see here that this isn't right. But just getting them to think about, how do you know if something's wrong? How do you develop the expertise to know if something is wrong?
Yeah, I wonder one way, I mean, there's no easy solution to that, but one way is to have the models compete against one another, basically ask multiple models the same question, and then have the students evaluate, which model is performing the best, why is it performing the best, and really try to analyze in detail what is being returned, because you can't do that unless you have some understanding of what's being returned and what's good or not good.
I think that like making the students go through that exercise with the LU decomposition. By the way, they did know the answer once they had a few minutes to review it. But I mean, it gets them to think about, if you get them to do something that's beyond their capabilities in a short period of time, and then you question them on it, they realize that they don't know things and that they've been trusting this machine to do something that they really didn't understand. That seemed to help set the tone of the class a little bit, and it did help them kind of move on a little. So maybe that kind of thing. But again, I'm going to just say we don't know what we're doing in this, right? There aren't best practices yet for teaching. They just don't exist. We're making them up as we're going along.
I definitely like what Stella said. In my quantum class, the professor said, you should always use Mathematica to do the integrals unless you don't know how to do them yourself. And that was the only time you shouldn't use Mathematica, because it's a super useful tool, and AI is kind of the same thing. And I like one of Mike's points about these students want to be there to be astrophysicists, and it's very tempting, if you like businesses and stuff, you can imagine that they don't care if their employees know how something works, as long as it works and they get the right answer. And it's who can get the right answer the fastest, and that's all that matters. But in education, it's just not, that shouldn't be the goal, shouldn't be the end goal at least. And it can be hard to instill that to students, because some people, like I was brought up with the mentality of just get the result, and it doesn't really matter how you get it. And it took a while to unlearn that. And if I started now with AI, I don't know, I probably would use it a lot more than I do now. But okay, that's just me rambling. Okay, so it's just about noon. If anyone thinks of any other questions, I'm sure you can email the speakers or anybody, and they'd be happy to answer. Someone asked about the slides. I don't think we generally make them available, but I think, like Alice said, the video of this whole thing will be posted on YouTube eventually, and so you can go there and page through the slides one by one. So yeah, I think that's it. It's noon. So yeah, thank you again to all the speakers, and thanks everybody for coming. And I think that's, if there's any announcements. So yeah, I guess that's it. Thank you all.
Thanks, everyone. That was fun.